Okay, so we have finished the topology unit, and now our next unit is on algebraic manipulation or techniques or concepts, something like that. And my understanding is that in year 9, you've already done some work around this leading up to where we are now. So what I simply want to do to start with is I want to just frame the picture, I guess, with some big ideas and stuff. And then get us to get stuck into doing some practice work. Now, the idea is that what we do in Maths Extended in this unit is the stuff, the more difficult stuff that you didn't get an opportunity to do in your regular maths class. Because I'm not a regular maths teacher, just tell me if I'm pitching it too low or too high, please. Don't just sit there and like that. Just tell me. It's going to be pitched a bit low to start with, only because I want to get the context right. But then once we get into it, you just need to tell me if you need more challenging stuff or whether it's too challenging. So keep that in mind. I want to start off by, as you can see here, the success criteria for today is that you're going to, I'm going to spend a moment talking about the difference between those two terms there. We've got simplifying and solving. And I find that students, even my maths methods students in grade 11 and 12, they often do confuse these kinds of words around. And you're going to do some fundamental expansion work, but hopefully doing problems that are a little bit beyond what you did in class, I hope. Like I said, we're starting small just to get a sense of it. So here's a problem I want you to work on. Whoops, there we go. So there may be opportunities where I might get you to do a little bit of problem solving while I'm teaching. So just scribbling it into your workbook is all I mean. And I'll tell you if I think you should be putting stuff into your summary book. But this is just a workbook thing. So you've got a problem here. The problem is based upon the amount of, let's just say you've got a widget factory. And the widget factory produces small fluffy toy bunnies. They're pretty special though. They cost $120 per bunny. Because you can't just get, it's made from premium fake fur, these toy bunnies. So the profit equation is 120x, where x is the number of bunnies sold, small, fluffy toy bunnies. No real bunnies were harmed in the making of this example. 120x minus 6,000. And the company wants to know, what's the break-even point? First things first. What do I mean by a break-even point? This is just a knowledge recall, which you may or may not know. Perfect. Which means that the profit is 0. So in other words, I'm asking, for what value of x will the profit be 0? Go. You've got a workbook, you've got a pen. Don't call out the answer. Figure it out. And for those that are staring at me blankly, oh my goodness, the numbers are a bit big, but and I'm not having a go at you, but I'm just saying, this is grade 8 work, solving this. This is grade 8 work. Don't look for a trick. There is no trick. I've got somewhere I'm going with it, that's all. Nick, you're up? Man, you got a pen? So shall I just get you some paper to scribble on? What? Why? Why are you guys not coming with books? It's like, I've got a sore foot, so you're making me walk further. It's rude. More up here if you need it. Did I miss something though? You don't have to answer this, but it's really weird how 4 of you didn't have any paper to write on when you're coming to class. Is it because you're used to doing the computery stuff from the last unit or something? I'd be keen to know why. It just seems really weird that you guys didn't come to a class with anything to write on. Okay, I know that some of you only just got the paper, and I apologise if you're watching this video back and you just had 2 minutes of me ranting about people not bringing paper. I'll give you another minute to finish off the problem. So know that if you've got an answer, you've only got a minute to wait. Here you got an answer? Yep. Answer. Oh, I thought you wanted to show me something. Just write on it like a normal piece of paper. Okay, that's enough time. What was that from? Man, it's going to be one of those lessons, is it? So, raise your hands if you got the answer 10. Good, because that wasn't the answer. Hugo's going to take us through how he worked it out. Go for it. Oh, sorry, draw tool, and you can just lean on it. You don't have to. Hover your hand over it. Just pretend it's paper. Are you sure you got that around the right way? Yeah, because that'd be a fraction, right? 120 smaller. Yep. What'd that equal? Which is the right answer, right? Who else got 50? Hey, anyone do it in a different way that would like to show? Is this going to be one of those classes that just doesn't too shy to say anything, or is it because you did it the same way? Who did it? I promise I won't make you do anything you don't want to. Just out of interest, who did it the same way as Hugo? A few of you, and then some of you just don't want to say anything. Okay, that was good. Thanks, Hugo. And intuitively, all really good, all good stuff. You found the erase button, did you? So all good. If I were doing it, because I'm sort of like got a bit of an algebra brain, I probably would have gone. I know that the break-even point is when the profit is equal to 0, which means that has to equal 0. That expression has to equal 0. Then I would have added 6,000 to both sides. Oh, you didn't find a colour pencil, did you? I'd add 6,000 to both sides, and that would get me 120x equals 6,000. And this is when Hugo and I are going to start to agree now, because then I'd divide both sides by 120, and I'd get x equal to 50. And that's basically what Hugo did on the side there, right? 6,000 divided by 120, and that's what I've done there. Who did it like me, like an algebra equation? Yeah, okay, thanks. And if you had other ways as well, if you got 50, it's probably a legitimate way you did it, unless you just went 6,000 divided by 6,000 times 50 or something like that, to be very random. So yeah, we've got 50, and there's an algebraic process that gets us there. Now, you don't have to use algebra for that, not directly. Hugo and a bunch of other people didn't, but you're not always going to be in that sort of position, are you? That you can it was almost an intuitive way that you guys did it, those who did it just by going 6,000 divided by 120. It's like saying, well, 6,000 is what I've got. That's the startup costs, 120 per rabbit. So if I divide 6,000 by 120, that's how much would get me to 50. That would give me 50. So that's how many I have to say. So that's almost an intuitive approach. And there's nothing wrong with that. But then let's just say that you've got a rather complicated model which describes your profit. And I'm sticking with profit because numbers and money is probably easy to understand, but it could be a climate change model. It could be an engineering tension on a spring model. There are so many different kinds of mathematical calculations out there that having the skills to be able to solve an equation effectively is really useful. So here's this. It's a bit dodgy, I know. I'll leave it zoomed out actually. So you've got this one here, which is P equals, so P for profit and X for the number is 3 outside of X plus 1 minus X plus 2 times X minus 1 is the profit equation. Who knows why that's the profit equation? But basically this company started up and said, oh, here are all my things that I need to sell these fluffy animals. Maybe it's not just rabbits. Maybe it's rabbits and puppies, all toys, of course, and fluffy bees. There you go. So 3 different animals. Maybe it's 3 different animals. Maybe there are other factors that go into things that they're going to have to do in terms of setting up their business. So anyway, so they give it to their economists, and they come back with this as the equation for determining the profit at any given point. Let's just say, it's a rubbish example, but I'm just saying, let's just say. Then what we need to do is we need to be able to have the skills, have the mathematical tools in our toolkit in order to be able to do things like, what's the break-even point? Because I reckon, Hugo, tell me if I'm wrong, and I'm only picking on you because you just did that problem then a second ago. Would it be a fair comment to say that without doing any other calculations, that profit equation on slide 3, you can't intuit the same way? Yeah. Not really. So we need something in order to get us to that point, right? And that something is just your mathematical toolkit, right? That allows you to manipulate equations and expressions so that you can do stuff with it. And it's not always profit. It's not always even particularly practical. It may be that it allows you to solve more complex maths problems. And when you can solve more complex maths problems, you can do stuff in higher order science, higher level science, and all that kind of stuff. So it might not be just about profit-making business, but it gives us something that we can imagine, I suppose. Okay. So what is the toolkit? In terms of algebra, if I talked about an algebra toolkit, I'll get the ball rolling so you can see where I'm coming from, or techniques. What are the techniques or tools that we tend to utilize to muck around with expressions? I'll start with one. I'll start with one so you can get an idea. I'm not looking for rocket science here. But one thing that we need to be across is like collecting like terms, right? So I need to know that if I've got 3x and I've got a 5x, that I know that I've actually got 8x by combining them together. But if it's 3x and 5x squared, I can't combine them together because they're not like terms. So we need to know about collecting like terms. What other tools do we have in our toolkit? Expanding, thank you. Expanding brackets, yeah. Yep. Factorizing. What else? Simplifying. Yep, great. You're on fire. What else? That'll do. What you identify is some of the really big ones. Not so much collecting like terms, which is what I put down, which is like just a really fundamental technique, but it is a technique. But expanding and factorizing are 2 of the big ones. And simplifying is the result from expanding, really, usually. Because if we can build on our tools of expanding and factorizing, then we'll be able to handle more complex algebraic expressions. So that's what we're going to focus on over the next few weeks. Expanding and factorizing for the most part and improving your techniques here. Because If I talk about an algebra toolkit, inside that toolkit, I pull out the expanding bit. That's actually not a tool itself. That's actually a selection of tools as well. And I don't know what you've done in regular maths, but have you done perfect squares in regular maths? That's a special tool, isn't it? It's an expansion tool and a factorizing tool. Have you done difference of two squares, dots, sometimes called difference of perfect square? No? X squared minus y squared equals x minus y times x plus y. Doesn't sound familiar, but maybe. That's another tool. Binomial expansions like a plus b times a minus b, a plus b times 2a plus 3b. Yeah, so that's another tool. So box method, that's another tool. Beak method, that's another tool, but does the same thing as the box method. When you get into grade 11 and 12 maths, there's like difference of sum of cubes, for example. What else? You've also got just a whole heap of other tools, is the point. So what we are doing in our mathematics journey, I suppose, is we're continuing to add to this toolkit so that when you see a problem, you've got an efficient method for solving it. Now, I did say here on slide 1, I can explain the difference between simplifying and solving. They both start with S. What is the difference between those two? If I ask you to simplify an expression, what does that mean? Yep, that's good. We talked about fractions. If I said simplify 4 over 6, what would that be? Huh? 2 over 3. So that's a simpler fraction, but it's the same value. So simplification does not change the value, but it's really hard to explain it without using the word simple, isn't it? But it normally takes an expression and makes it look a lot simpler. And we use techniques of expansions, factorizations, and collecting like terms to make it simpler. What does solving mean? This is where I do want to get precise. Go for it. Keep going. That's like 75% of the way there. Finding the answer. To solve something, here's the first thing. To solve something, we need one of these, aka an equal sign, right? It's not quite true, but it's true enough for us. If there's no equal sign, there's no solving. If I said solve 3x plus 2, what would you tell me? Correct. How do you solve 3x plus 2? You can't, because there's no sense of, well, what values of x are we looking for here? But if I said solve 3x plus 2 equals 5, what could you tell me? I'm really worried that you're not too sure how to solve that. Someone said it though. Yeah. Okay. X equals 1. So when you see the word solve, what you're really saying, and I'll just build on what Hugo said. So what you're really saying is finding all possible values for x so that the equation is true. Does that kind of make sense? So that the equation is true. And where it gets tricky, and we'll look at that in this unit, is that if I just pick something like x squared equals 9, what does x equal? Okay, you've just got 1 out of 2 marks. Why? Positive and negative 3. Yeah? Because although 3 is an answer, 3 squared is 9, so is negative 3, because negative 3 times negative 3 is positive 9. So when we solve an equation, we are simply answering the question, for what values of x would this equation be true? So when we had a profit margin that we've got here of profit equals 120x minus 6, what is the break-even point? To be precise, what we were saying is, for what value of x is 120x minus 6,000 equals 0 true? When is it true? It's true when x equals 50. It's not true when x equals 50.1. It's not true when x equals 51. It's only true when x equals 50. Does that make sense so far? Okay, so when we have something slightly more complicated, like 3 outside of x plus 1 minus x plus 2 times x minus 1, when we have something slightly more complicated, then we need to be able to answer similar questions, but using more higher order techniques. But ultimately, if I said, what's the break-even point of this equation, then what I'm really asking is, for what values of x does 3 outside of x plus 1 minus x plus 2 times x minus 1 equal 0? Okay, all right, that's the big picture stuff. So we've talked about that. There's some techniques. Collecting like terms, expansions, and factorization, and simplifying is not on this little list, but nevertheless. And what we're going to do now is we're going to have a crack at we're going to have a crack at looking at this expression here. So this is just to test you out to see how good you are, I suppose. I'm going to pause the video, and I'll give you 2 minutes to see if you can. Am I going to ask you to simplify this or solve this? Which one? Simplify is right, because you can't solve it, can you? Can you? No, but why not? No equal sign. Okay, so try simplifying this, and you got 2 minutes. Okay, let's have a little look at this. I've underlined the bit which I think everyone would be absolutely legitimately fine with anyway, which is 3 outside of x plus 1. So that would be 3x plus 3. Okay, so if I'm going to simplify this, I'm going to have to be able to do things like collect like terms. I can't collect like terms while they're inside bracketed expressions because of BODMAS, brackets first, which means they're sort of locked in there, which means I'm going to have to expand it if I'm going to get anywhere. And so I've done an expansion here where I've just gone 3 times x is 3x, 3 times 1 is 3. Now, I'm going to zoom out and leave it zoomed out. And the next bit is the x plus 2 times x minus 1, which I will do in angry red. And I wanted to just show you 2 different methods, because as maths extended students, like normally with regular maths, you kind of want students to just have one technique and just use it because it's the most convenient thing to do, I suppose. Not convenient, it's probably the most safest thing to do. But because you're maths extended students, I would like to just go through 2 different techniques. You would be aware of them both, even if you're not aware of the language. So first of all, box method for this one is that you draw the box. It's great. It's graphical. If you're visually minded, the box method is really good. Plus, if you don't like the box method, you should at least be familiar with it because it's really, really useful in maths methods in grade 11 when you do what's called the reverse box method for polynomial division. So absolutely keep up your skills with box method. But we know what we do. We put one of the binomials, by the way, this is what this is called because there are 2 terms to it, bi meaning 2. So binomial, binomial. And then I just fill in the little boxes. So I've got x squared, and I've got 2x, and I've got minus 1 times x, and I've got minus 1 times 2. And then I read along the diagonals, and that gets me x squared minus x minus 2x is minus 3x, and I've got minus 2. Everyone have I stuffed up? Yeah, thank you. No. Have I stuffed up somewhere else then? Minus 2x, that's where I made a mistake. No, sorry, I did not make a mistake there. I made a mistake here, didn't I? Thank you. Plus x. But process-wise, does that make sense to everybody? That's the standard box method. Let me show you the chicken beak method. Its strength, the strength of the chicken beak method, which I'm sure you've basically seen, is that it's not as the problem with the box method is that it's quite chunky in terms of the space it takes in your book to do. But if you're visual, it's really good. But the box method, the chicken beak method, basically says that ultimately what you do when you're expanding 2 brackets is you multiply everything in one bracket by everything in the other bracket, right? And to keep track of it, you do this. Oops, that's my eraser. X times x is x squared. X times -1 is minus x. 2 times x is 2x. And 2 times -1 is -2. Then I collect like terms, and I get x squared plus x minus 2, which is the same as I had on the left there. It's called the chicken beak method because if you have a look at the look at this, this is kind of like the top of the beak. This is like the bottom of the beak. So it's a chicken beak. Like yeah, you could, you know what, you could call it the claw method, like a crab claw kind of thing. Yeah, so you could call it the crab claw method if you want. I call it the chicken beak. Well, I didn't come up with it, but yeah, chicken beak method is what I call it. So you can use either method. I'm happy with you to use either method. But if you do prefer that sort of this way of doing it, where it's just all, you know, no big boxes and stuff, do make sure you at least know how to do the box method. Okay. All right. So let's put it all together. And oh man, I'm just going to put in a new page here. Give me a ticky. Okay. Sorry. So there's our techniques. Putting it all together, we would have 3x plus 3 in blue. So there's the 3x plus 3 in the blue. And then we would have x squared plus x minus 2 from the red. So x squared plus x minus 2 in the red. And then we have our plus 3 on the end, which we haven't dealt with yet. Now, importantly, is that if you look at the problem, we are subtracting these two things multiplied together. So when we come up with our expression, we need to make sure that we are subtracting x squared plus x minus 2. But we're not subtracting x squared, we're subtracting all three terms, right? X squared plus x minus 2. So we need to put the brackets in to tell BODMAS effectively, or to be using BODMAS to say these three terms are kind of like kept together. So the next line would be 3x plus 3 minus x squared minus x, and then minus 2 is plus 2 plus 3. And then finishing it off. And as a matter of standard practice, if it's just one variable, have it in descending powers of x with the highest power of x on the left. So I would say that's minus x squared. 3x minus x is 2x plus 2x. 3 plus 2 is 5 plus 3 is 8. So I'm left with x squared plus 2x minus 8. And now it's simplified. What do you reckon? So there's a whole bunch of techniques there, but really, I mean, I just took 10 minutes to do that, but you should have been able to do it in under 2 minutes easily. It's just that all my explanation just makes it feel like a rather tedious, drawn-out process. But ultimately, what I find is that students who can use these tools quickly can solve more complex problems as a result. So if you were slow solving that, or you're not too sure of the steps there, then make sure that you do some practice around it. But this is I think this is one of the important takeaways here, is whenever you're dealing with a subtraction, remember your brackets. Take an extra step to do it with brackets in so you can get somewhere. Alrighty. Any questions about that before we move on? So, just to bring it home in terms of what I asked you to do, have I made the problem easier? If I go back to the first problem and say, this is my profit equation and we need to break even, we know that we have to set it equal to 0. So I've got here minus x squared plus 2x minus 8 is equal to 0. That would be the profit equation. Is that now easier to solve? Not yet. It's still not really. I've kind of tidied it up, made it look a lot simpler, but ultimately it's actually not much easier yet. But this is what I can do. And we're going to do this later on in the course in the expansions part, in the factorizing part of the course. I'm focusing on expansion, so don't worry about taking this. Logan, you got it, so that's really good. Yeah, go on. Thank you. So you got this, so well done. And other people might have got it, but didn't show me. So but regardless, don't stress about if you didn't. I can do things like this. I want to factorize x squared plus 2x minus x squared plus 2x plus 8. But factorizing with a negative x squared is no good. So I'm going to multiply both sides by negative 1. That'll give me, don't even bother writing this down, x squared minus 2x minus 8 is equal to 0. So a positive x squared is quite helpful. Okay, good so far? Now I'm going to factorize this, and I'm going to use what's called monic factorization to solve this. And I can see that x minus 4x plus 2 will equal 0. And I can now use a special rule called the null factor law, which we will look at. Have you looked at null factor law in regular maths? Null factor law simply says if I've got two things, don't worry about how complicated they look, multiply together to give me 0, one of them must be 0, right? Like if I said 3 times what equals 0, what would you tell me? What about 10 times 0? What about pi times 0? What about x times what equals 0? 0. Pi times what equals 0? 0. So both of those things, one of those must be equal to 0. So what are my possibilities? X minus 4 equals 0, which means x equals 4. Or x plus 2 equals 0, which means x equals negative 2. So there are my two possible numbers. One of them can't work for my equation. Which one can't work? Negative 2, because I can't literally sell negative 2 toys. That'd be like I get a refund of 2, and that doesn't make sense. But x equals 4 does work. So if I sell 4 of them, I'm going to break even. If I sell more than 4, then it's even better. So there's all my algebra toolkit all coming together over these couple of pages here. I need to know how to expand, simplify, factorize, solve by setting it equal to 0 using another law called the null factor law. A whole bunch of tools that you need to learn to be able to pull out of your toolkit. Just like any tradesman will be able to not just pull out a hammer and use it to solve every single problem. They might pull out a hammer and a screwdriver and a saw and all that kind of stuff and use them all to fix the problem that they need to fix. And we're the same. We need to develop these tools so that we can use them all together to solve problems. Taking it back a step, and this is where I want to focus on for the rest of today, and I've spent too long, I apologize for that. I want to have a look at this expansion here, and it's the expansion x plus 1 multiplied by x squared plus x minus 1. Now, my understanding is that you have not solved problems like this before. Am I right or am I wrong? This is a binomial two terms, multiplied by a trinomial, 3 terms. Okay, basically, chicken beaking and box method works for this as well. You just need to have more boxes. I'm just going to show box method. I reckon you can figure out chicken beaking if that's what you want to do. I'll do it in slide 10. So instead of having a 2 by 2 box, guess what? 2 by 3. So I have a 2 by 3. This is something you could put into your summary book. I've got x plus 1 down the side, and I've got x squared plus x plus 1 up the top. So I just need to break it into 3 sections. And now I do the same thing. I just basically fill in those boxes and then collect like terms. So I'll do it in blue just so it stands out. X times x squared is x cubed. X squared times 1 is x squared. X times x is x squared. X times 1 is x. Just filling out those boxes. I'm only worried about the boxes. I'm not worried about what it all means. 1 times x is x. 1 times 1 is 1. I'll stop there for a moment and ask if there are any questions about how I set it up or how I filled in the blue boxes. And give you a chance to copy it down. All good? So the power of the box method, which doesn't really get uncovered until we do these sort of longer ones, is that to collect like terms, we simply go across the diagonals. Did you notice that the diagonals are always like terms? So this is the only x cubed, and it sits there in the corner. These are my x squareds, these are my x's, and there's my what's called the constant term, the term with no variables in it at all. So the final answer, the collecting of like terms, is just adding up across the diagonals. So we end up with x cubed, and then add along the diagonals, x squared plus x squared is 2x squared. Add along the diagonals, x plus x is 2x. Add along the diagonal, there's only one though, which is 1. So it's x cubed plus 2x squared plus 2x plus 1. That's basically it. There is a technique with the chicken beak method. There is a setting out technique which helps you collect like terms really easily too. But I'm not too sure how many people I'd be talking to if I went through the chicken beak method with this and the formatting. So if chicken beak method is something that you think you'd want to do yourself, once you've done a problem or two, maybe come and show me, and I'll show you how you can set it out just to make collecting like terms a really straightforward process as well. So I'll put this onto Google Classroom, this worksheet I'm about to hand out in class. But yeah, what I'm going to get you to do now and then continue working on this in class is a worksheet which has some of these more complicated expressions. So I'll tell you which ones to do in a second, because I don't want you to do them all. And I'll put it onto Google Classroom which ones to do as well. So it's a single page worksheet here with all the answers on the back. You don't have to do all of them. So I'll stop the video now and I'll come out and give you a sheet. Don't start until I've told you what to do though.